we're good to go. So, good afternoon, everybody. Apologies for being a few minutes late. So this is the talk on both reprocessing and recycle. So I'm going to cover a couple of key topics that often when people talk about reprocessing, they often throw in the phrase recycle without actually explicitly mentioning it. You can reprocess without actually recycling the material that comes from that. So I'm going to touch on both topics just to make sure that we fully understand the totality of the ground we need to cover. So just what I'm going to talk about is I'm going to introduce some of the fuel cycle options. There are multiple out there, and there are several hundred, if not thousands, of options. I'm not going to cover all of them, of course, but I'm going to cover a few of the major fuel cycle options that are being considered today and for the future. I'll then move on to talk about reprocessing, why reprocess in the first place, what's the benefit of that, and also then talk about some of the stages involved in reprocessing. And then I'll move on to recycle. Why are people considering recycle? What are the advantages and purposes in recycle? And in particular, we talk about reprocessing the plutonium and the reprocessed uranium. You can reprocess minor actinides, but that's not a subject to this topic. But you can, just again for background, you can actually recycle the minor actinides too, but I won't talk about that today. And then what I also wanted to do was just touch on some of the non-proliferation issues related to reprocessing and recycle. Again, that in itself is a huge topic that we don't have time to cover today, but I will touch on some of the elements of that and how, despite kind of popular belief, reprocessing can and is being done under a safeguards regime, and there's no issues associated with the non-proliferation. And then finally, summary and conclusions. So, despite what you may think, I have no accent. It's you guys that have the accent. So, I actually have been with ONL just for the last about 2.5 years. Prior to that, I was with the UK nuclear industry, as you can probably tell by my accent. I'm not from East Tennessee. I'm actually from the UK. So I work for a company called British Nuclear Fuels Limited, BNFL, who actually no longer exists. So depending on the age of the audience, you may never even heard of them. But BNFL was an equivalent company to Areva. So BNFL were involved in everything from fuel fabrication to operating reactors, to then taking the spent fuel and reprocessing it. And that was a commercial business. For many years, BNFL was the largest earner of Japanese yen, for example, for the whole of the UK, because of reprocessing. And then dealing with the waste management issues and the back end of the fuel cycle and so on. That was BNFL's business. So I used to work for that organisation. And in fact, my background is not reprocessing or indeed anything to do with the fuel cycle exactly. My real background was reactor analysis, reactor physics, but very quickly I got involved in BNFL's broader business, which was plutonium management. And as part of plutonium management and the potential to put plutonium and recycle that in reactors, which I'll talk about shortly, then suddenly you get involved in much broader aspects of the fuel cycle, including weapons plutonium disposition and so forth. And then I spent a lot of time working my way up to eventually I was part of the UK National Nuclear Laboratory, where I was the technical authority for reactors and fuels, advising the UK government on plutonium, as I mentioned, but also a new nuclear build, advanced fuel cycles, thorium fuel cycles, and a whole range of other things. I also got involved in a whole range of academic lectures and so forth, and I was a Royal Academy of Engineering professor at two of the leading UK universities. But in general, my interest in nuclear are very broad and wide. I'm very fortunate that I've done everything from press my own fuel pellets. I've seen plutonium being fabricated into new fuels. I've seen commercial and fast reactor fuel sheared and reprocessed. I've been very, very fortunate in my career. So hopefully I'll try and explain some of those operations and experiences that I've got to you today. Okay, so introduction to the fuel cycles. What are some of the drivers for energy supply? If you just think for a few minutes and put yourself in various people's shoes and look at these different perspectives, whether that may be an operating utility, whether that may be a government, a vendor, whoever it may be, there's a whole range of different things that you need to think about in terms of energy supply. And the classic one everybody would typically think of would of course be the economics. You might look at reducing the capital cost, you want the fuel cycle cost to be lower, and of course overall it has to be affordable, otherwise you wouldn't consider it. So that's one of the drivers for future fuel cycles. Sustainability is becoming ever important. The US is in a very fortunate position that it has a huge supply of natural gas and oil Not so much on uranium, only produce something about 9 or 10% of the world's uranium, but something the US will need to think about in the future, not too distant future, is sustainability and coming up with future energy options, including nuclear, that are sustainable. And I hope we all agree that we need to do more with the resources we have rather than just waste them just simply because we have them at our disposal. Waste management is something that everybody always talks about with nuclear, and quite rightly so, and I'll touch on some of the details later, but some of the drivers for future energy growth from a nuclear perspective are things like repository performance, making sure something like intergenerational equity, it's called, we don't pass on our problems of this generation onto future generations. So dealing with the waste is incredibly important, and how we fix that. Of course, safety is really important, and that includes not only operational safety for the public, but also security and physical protection. And of course, it wouldn't be right to talk about these things without thinking about proliferation resistance. But also, what does that mean, non-proliferation? Well, it means making sure bad guys don't get the materials, but also they don't get the technology that they can misuse, and also the knowledge that they can misuse. We have to protect all of those. And then the final thing we need to think about with energy supply, particularly again for the role of nuclear, is broader than just electricity. And again, this is something other parts of the world are desperately thinking about. For example, if you look at the water demands around the world, and the ability for potable water in Africa, it's a very, very small percentage of people who have the access to clean water. So things like nuclear for desalination is incredibly important, not for electricity generation. In some parts of Europe, in the Baltic states, district heating is incredibly important, and also things like hydrogen economy, even for transport. So all these things are broader concerns, questions, challenges we have to address when thinking about nuclear. And what that means is when evaluating and considering a fuel cycle option, we need to think of it from all these people's perspectives. As I said, the operators, the governments, the international agencies like the IAEA, but also regulators, vendors, that people want to make money out of this, as well as good for the good of mankind. So the reason I mention all of that is that if we're not careful, what we end up focusing on is, what's the most technical, the best technical solution, not necessarily the best economic solution, or we don't necessarily think about it broader in terms of how else this nuclear fuel cycle can have benefits. So that's why I wanted to mention that up front. So I'm sure most of you probably have already seen something like this before, but I just wanted to make sure we were all on the same page. If you look at the current US nuclear fuel cycle, it's pretty much what's known as a once-through fuel cycle. So starting from the top left, we mine and mill the uranium ore. We then convert it into a powder that we can then turn into a gas to enrich from the natural U-235 of 0.7%, typically enriching to something like 4.5–5% in most current commercial light water reactors. We then make that enriched product into fuel pellets, and then we put those into assemblies, generate electricity. And then this is where the fuel cycle kind of diverges at this point. We have two options that I'll start talking about, but in the US, the direct route currently is store the fuel for a period of time in interim cooling at the reactor sites in pools, and then potentially have to dry store that as we fill the fuel pools up at the reactor sites, and then finally ultimate disposal in something like Yucca Mountain. And again, that's a whole other topic of what Yucca Mountain or alternatives look like, but that's not subject to today's talk. But the key thing here is just to bear in mind that when you look at the once-through fuel cycle, everybody thinks of that as being complete. Well, in fact, it isn't. We as an industry, as a nuclear industry, haven't yet even demonstrated a once-through fuel cycle because we haven't yet done the ultimate disposal part of it, which is one of the major challenges for nuclear. So when people start talking about reprocessing and all these fancy future fuel cycles, you would also have to bear in mind that we haven't yet done the once-through fuel cycle completely either. So there's still plenty of challenges there. So if we compare and contrast then so I just talked about mining, milling and extraction, converting to uranium hexafluoride, enrichment, then on to making fuel, and then all the way through to reactors. What we call that is the front end of the fuel cycle. So anything from leading up to the reactor is typically known as the front end of the fuel cycle. If you have a front end, then of course naturally you have a back end of the fuel cycle, and this is where they said that the options kind of diverge. So what we can do is we can reprocess or we can store indefinitely. And as I just illustrated on the previous slide, the store indefinitely is the current once-through fuel cycle, the US fuel cycle. If we're to reprocess, in Europe, we typically have generated 3 levels of waste streams known as low-level waste, intermediate-level waste, and high-level waste. The classifications aren't so important, but I just wanted to demonstrate there's a whole range of waste streams. And if two of the major byproducts we get from reprocessing, though, which we can do something else with subsequently, i.e. the recycle part of it, is we generate uranium and plutonium from the spent fuel. And typically we can store that, and that's what's been happening, for example, in the UK, has been storing that. But alternatively, we can take that uranium and feed that back into the uranium fuel cycle and re-enrich and so forth. Or we can take the plutonium and make that into what's known as MOX fuel, mixed oxide fuel of plutonium and uranium, and directly put that in through a fuel fabrication process and back into the reactor. So, and those are the stages I'm going to go through in a little more detail, but I think it's worth giving you an idea of what that layout looks like before we start in the details. So, there's a couple of different phrases you sometimes hear with fuel cycle options. Simply put, they're either open or closed is the two options. So the open fuel cycle, or the once-through fuel cycle, as I said, is the US. Basically take the uranium ore out of the ground, make it into fuel, put it in a reactor, put it down the hole in the ground. That's known as the once-through or the open fuel cycle. The full recycle option, but this isn't where we are today, this is where you need fast reactors and these fancy future reactors, is we again do the same thing, recover the ore, make the fuel, put into a reactor, but now we then recycle. We separate, first of all, the good stuff and the bad stuff. The bad stuff we don't want, we put it down a hole in the ground in the repository. The good stuff we recycle as fuel. And that's known as the closed fuel cycle. So the open fuel cycle, no recycling or conditioning of the used fuel, which really means low uranium utilization. On the other side, though, the closed fuel cycle is we can multiply reprocess and as many times as we can the materials, and also transmutate the actinides, the minor actinides, as I mentioned, is one option, and that's a complete uranium utilization. It's as much as we can possibly do. And just for your complete understanding, there are stages in between, which is typically called the modified open fuel cycle, or limited recycle as it's also known. And that's pretty much what France is currently doing. France is right in that middle one in the modified open, because what they're currently doing is they're taking the plutonium and the uranium and recycling it, but not to the extent where you can do that infinitely. They're only doing that in light water reactors. And again, I'll touch on some of the details later, but you can only do that once or twice because of the fissile quality of the material recycling. And then the minor actinides and the fission products are then disposed of directly. So that's where it's modified. So some of the drivers that are being considered right now are things like we need better utilization of limited resource. Despite what people say, there are only finite resources out there for uranium, just like oil, gas, and whatever. If you look at the OECD and the IAEA, they quote something like 60, 80, maybe up to 100 years of known uranium resource that's available today based on a certain growth scenario for nuclear over the next few decades. But the important thing to bear in mind with that is that that's what's known today. Every time somebody's gone and prospected and looked for new uranium, they've found it. But you don't go and look for it unless there's a shortage, and there is not a shortage today, so people just don't go and look for it. Same with any other commodity. The second driver for these advanced fuel cycles, we want the back-end fuel costs to be lower. Things like the waste and so much I'll touch on shortly, and the impact that may have on repositories and the cost that drives your repository. There's plenty of good reason why you want to recycle. There is a lot of perceived proliferation risk posed by reprocessing and plutonium separation. I say perceived because the risk really is there for sure, but it's not a greater, the perception is almost that that's a greater risk than other fuel cycles. And again, I'm not going to go into it in detail now, but if you Google or look up work by a guy called Charles Bathke, then you will see things like material attractiveness, figure of merit, where basically their analysis by people like Los Alamos and the other weapons labs illustrate that all fuel cycles, all of them, generate material that is potentially bomb grade material, weapons grade material. What that simply means is, therefore, every fuel cycle needs safeguards and security. So that's not to say plutonium is any worse than anything else. For example, in the uranium fuel cycles of today around the world, where plutonium is not separated, we still have to have safeguards and security. So just to illustrate, there is not a great game changer there. We're also trying to simplify the number of waste streams and reduce the impact on the environment. And also in the meantime trying to maximize the benefit and the improvements we have in the existing fuel of today. One point to bear in mind though is that for these ultimate long-term future fast reactor fuel cycles and all these, as I mentioned, these completely closed fuel cycles, you do rely on not just the fuel cycle technology but new reactor technology. So there's an awful lot of research, development and commercial case to be made. So things like developing future fast reactors or molten salt reactors are part of that. Okay, so that's just trying to set some of the scenes, some of the language, and I'm going to go now into more detail and to talk about each of the components of reprocessing and recycle. So what is reprocessing first of all? Well, reprocessing is the separation of the reusable fissile material, typically the uranium and plutonium, and the reuse of that, the recycle of that in new nuclear fuel. In many ways, this reprocessing and recycling nuclear is no different to the way we hopefully all at home recycle our garbage and extract the good stuff, the plastics, the bottles from the traditional household waste. This is very similar. It's just taking the good stuff out, separating the good from the bad, and recycling the good stuff. So this is what's essential to close the nuclear fuel cycle. You have to have reprocessing. Of course, if you fission fuel, uranium or plutonium in a reactor, that fission process generates fission products, and we want to get those out of the fuel. We don't need those anymore. They're definitely a waste product. We get those out, we immobilize and dispose of that, and all of that separation process is all based on solvent extraction, a chemical process known as Purex, which basically stands for plutonium and uranium extraction. And that's the baseline industrial process of today that's used in the UK, in France, and in many other places. There are other options other than Purex, and again I'll touch on those later, but things like COEX means the co-extraction. So where there are concerns that maybe plutonium could be diverted for a weapons program or some other mission, then future fuel cycle options are looking at co-extraction of uranium and plutonium together so that you don't generate pure plutonium. And also looking at things like where the plutonium is kept with the minor actinides and the fission products under a Urex, and there's a whole range of other things. And again, I'll show you some of those later. And this just to demonstrate the complexity of the various product streams. I'm not going to go into that, but you can read that at your leisure later, just to show you the different options. And there's all the subtleties of Urex +1 and all the various other things. Again, I'm not going to go into. So why bother reprocessing is often a question we hear, because not every country does it, and why would they? Well, the first thing is, historically, it's typically been because of the weapons program. If you look at the US has reprocessed historically, primarily because of to extract the plutonium for the weapons program. The UK also did exactly the same thing, was all about reprocessing to get the plutonium out of the fuel for the weapons program. So that's part of it. But back to what I started the talk with regard to, and that's kind of energy policy and energy supply. One of the things that, for example, Japan faces is that Japan has no indigenous oil or gas or coal. So it has to do something to ensure energy independence, and that's why Japan is focusing very much on reprocessing and recycle. When they buy their uranium, they want to maximize the use of that uranium, and things like reprocessing enables them to do that, maximize their resource. I've touched on this one already, resource conservation and recycled fissile materials. Reprocessing, in fact, does have some proliferation resistance benefits with regard to either the burning of the actinides in one sense, but also if you have separated plutonium for all sorts of reasons, then you can reprocess and recycle that to destroy that plutonium too. So that's another way of looking at it. You actually are destroying the plutonium. Something I'll touch on and show you a couple of graphs shortly, some more detail, is you can use reprocessing to minimize the volume of waste, volume of material that you're going to put down the repository for ultimate disposal. And then similarly, spent fuel management, you end up with, in spent fuel, you end up with a lot of fission products and potentially the weakness of the spent fuel. So potentially by reprocessing, you remove that those fission products, you remove that weaker structure, the fuel pins and fuel pellets, and you then kind of recondition, in a sense, into a repository condition. And then with somebody like the UK, one of the reactor options they have was the Magnox reactors, the old graphite reactors. And in fact, they have to reprocess that material because the cladding that surrounds the fuel is actually a magnesium alloy. And it has to be kept under water because magnesium, we've probably all done this in high school class, try to light magnesium ribbon, it burns tremendously. That's not exactly a reaction you want to see in a nuclear fuel. So that means you cannot allow it to be exposed to air, so you have to keep it under water. Unfortunately, when you put magnesium alloy under water, it dissolves in water. So therefore, that's also not a good condition. You want your fuel to be dissolving in water. So that's why they have to reprocess to put it in a much more stable form. So there's some of the drivers outside of economics. So the obvious one to answer then, well, is reprocessing economic? And the answer is no. Well, yes, but the answer actually is maybe. It depends on so many different things. It's not easy to say for sure. And that's why some countries have gone down that route and others have not, as well as the drivers based on country policy. So it depends on a whole range of things. Often the approach to economics is one of the drivers. The problem with a lot of economics, for anybody who's done any, is particularly for nuclear economics, you get this thing called discounted cash flow analysis. And what that really means is that anything out in the long time in the future, the value of that money is discounted away. So what happens is if you have an outlay in the future of, say, $500 million for a decommissioning project, or a repository is needed, what happens is if you put a small amount of money aside today, that money will grow by putting it into the banks or investing it and so on. And so you don't need to put your $500 million in the bank today. You just put a small amount of money and watch it grow over the next 50 to 100 years. So that same approach is applied here, where what happens is that all the direct disposal costs are put off so long in the future that it discounts all the actual costs away. The costs kind of disappear. The other thing that drives the economics of reprocessing as a yes or no is the price of uranium ore. If the price of uranium is very low, which usually coincides when there's lots of uranium around, then if the price is low, then why recycle? We don't need to be so concerned with the availability of that resource. But if the price of uranium goes up, then suddenly the value of that reprocessed uranium and the value of plutonium also goes up to recycle. The other thing as well is that you can achieve higher burn-ups in light water reactors. What you tend to find is that if you need to get more energy out of your fuel, you need to put more fissile material in there. In the case of uranium, you have to pay for that by enriching it. The more you enrich, the higher the cost, and that goes up exponentially. Whereas with plutonium, if you've already made the decision to separate that plutonium out, plutonium is free issue at that point, because it doesn't matter when you manufacture a fuel with plutonium fuels, whether I put 1% plutonium into that fuel or 10% plutonium into that fuel, it actually doesn't increase the cost of that fuel production at that time. So what it means is I can get more energy out by doing that. Cost of spent fuel, that obviously drives things also. But in general, the cost of the two, keeping irradiated fuel in a repository or the cost of reprocessing, they're comparable. And this is something, again, I'm not going into the details here, but this is some studies from the OECD, and I just updated some figures from 1993. But this just shows and compares the direct disposal on the left with reprocessing on the right. Of course, all the front end of the fuel cycle components are exactly the same. It's only the pieces at the back end at the top of that histogram that changes. And what you find is that the front end costs dominate. About 80% of the overall fuel cycle cost comes from fuel costs, regardless of which option you choose. And if you look at these two examples, we've got a comparison of about 5.5 mils per kilowatt hour versus 6, as you can see on the left and the right. What the chart on the right takes no account of, though, is that the material that comes from reprocessing the uranium and plutonium, we can recycle and reuse that, and therefore that's an avoided cost of us having to buy more uranium. That's not in that chart. That equates to about 0.3. So when you look at the value overall, they're pretty comparable, within about 10% of each other. And of course, the things on the left can go up or down, the things on the right can go up and down. So within uncertainties, they're pretty much equivalent. So when we talk about reprocessing and recycle, which bits are we talking about recycling and which bits are we talking about throwing away? Well, In fact, more often than not, what's typically been talked about is just reprocessing and recycling the fuel pellets themselves, the actual fissile material and the pieces that are inside the mechanical hardware of fuel. But in fact, here at Oak Ridge, working on a US Department of Energy program, one of the things that's also being looked at is in fact recycling the zircaloy, the actual cladding that's in the fuel and the hardware, and actually recycling the metal as well as the fuel inside those metal components. So that's something else to bear in mind. It's not just necessarily recycle and reprocessing from a material of the fuel. But to me, this is probably one of the key takeaways from the message about the value or purpose of reprocessing versus direct disposal. Just forgetting the chart on the right hand side for now, just concentrate on the one on the left, the by weight pie chart. When we load fuel into a reactor, of course, it's 100% uranium. But when we discharge it after it's 4, 5, 6 years in a reactor, after it's been cooled and so on, what we see on the left hand side is then what the weight fractions are of those various isotopes, so various elements. So uranium still makes up the vast majority. Typically 96% of the 100% is still uranium. Then we've generated about 1% plutonium in that fuel. We've produced other actinides like curiums and so on. But of course what we've done is we've fissioned that uranium, and so we've got fission products, which makes up about 3%. The chart on the right hand side then shows you not what their composition by weight now is, but what the composition by radioactivity is. Now why is that important? Well, it's the radioactivity you can consider either as the dose to an operator, or the dose to the public, or the dose to the repository. Or alternatively, you can look at that as meaning the decay heat, the amount of heat that spent fuel is generating. So what you find is that the vast majority of that material in that spent fuel is actually producing hardly any of the decay heat or radiation in that fuel. It's in fact the majority comes from the fission products. So if you can therefore separate out those fission products, i.e. the very small volume, and concentrate that down, now you've got a much smaller volume to put in your repository, and therefore the demand on the repository is much less. Whereas if you were just to put the whole fuel assembly down there, you're actually filling a lot of volume for very little benefit. And so this is a slightly more complex chart, but if you bear with me, you'll see where this becomes important. Is if you look at the, hopefully you can see the arrow on here, but basically if you look at the total radioactivity, so what we're doing is we're plotting radioactivity on the x-axis, y-axis, sorry, versus time on the x-axis. What you see is that over time, it's actually the plutonium and the decay products that are kind of the long-lived things that stay around for a long while, and therefore they're the ones that are going to have a long-term impact on your repository. So if you can remove those from your fuel, and therefore they're not going in the repository, and you can remove the minor actinides and decay products and do other things with that, what you end up with is, instead of being a 10 to 100,000 year problem, you actually can now reduce this way over to the left hand side, where all you're actually doing by putting concentrating your fission products is you've actually now got a 300 year problem, because after about 300 years you're now back to that uranium ore level where you're back to that kind of background level of uranium ore radioactivity. Whereas if you didn't do that, it takes you 100,000 years or more before you get to those background levels. So that's what that graph just shows you. It's kind of showing what I said earlier in a slightly different way. So the US is considering how to move to one of these advanced fuel cycles today. One of the programs of work that's being taken part within the US Department of Energy is something called the Fuel Cycle Options Campaign. So we're looking at a whole range of fuel cycle options, whether that's with fast reactors or thermal reactors, with thorium or with uranium, and a whole range of other things. And again, you can find those reports and those studies on the web. But the key thing here for the US is those options are being considered. The once-through fuel cycle is still the fuel cycle of choice. It produces 20% of electricity in the US, so at the moment there's no point to move away from that. So again, I'm not going to go into that in detail, but just wanted to let you know there are other options out there that the US are considering today. So just to demonstrate some of the steps in reprocessing, and again I'll show you some pictures and some diagrams to bring some of this home, I hope. The first thing is, and what you're seeing on the right hand side is a picture of the Sellafield reprocessing plant in the north of the UK. So you're seeing the building right in the centre there with the kind of red chimneys, the red side, actually size of the buildings, they're not chimneys, that's the side of the building. That's the thermal oxide reprocessing plant known as Thorpe, that's at Sellafield in the UK. So at the bottom of that picture you see a kind of a square building. That's where the fuel is received and stored. Okay, so that's the first step, is receipt and storage. The second stage after that is what's called the head end process, and I'll show you some pictures and some schematics in a second. So the first step after it's been received, the material has been received and stored, is then to expose the fuel itself, the pellets themselves, from within inside the cladding. So the first thing that has to happen is we have to expose that fuel by shearing it and basically shaking out, removing the fuel from the inside. We then dissolve those fuel pellets in nitric acid. Of course, by doing that, we generate some off gas. We have to treat the off gas, and then we dissolve and treat the solids. The first two steps, that receipt and storage and head end, the steps are usually the same in terms of that they happen, but depending on the fuel type or reactor type, there may be some additional steps. And again, I'm not going to go into that, but I just wanted to flag that what you'll often see is, if you talk about reprocessing fast reactor fuel, the receipt and storage and head end processes will differ from what I'm about to describe now, but they are similar processes still needed. The third stage, after you've received the fuel, you've dissolved, you've chopped it up, is that you now need to chemically separate all those elements that I described. And then once you've separated them, then you need to purify them to put them in a form that can be reused if appropriate. And typically that's done using the Purex process, as I mentioned earlier, using solvent extraction, and that's with chemical separation. But again, just a little marker here, there are alternatives for things like fast reactor fuels, which is known as pyro reprocessing, using something like a molten salt or electro refining. And again, I'm not going to go into that today, but just to flag that there are alternatives. And then once you've gone through all that, then you'll need to store that material for potential future reuse. And the material that you're no longer going to use, you then have to do something with it, like waste treatment. So this is the flow sheet in a little bit more detail, starting from the left-hand side, going through spent fuel assemblies received, and then you cut and shear them, and you see the off-gas kind of goes upwards and so on. I'm not going to go into that in detail, just conscious of time, and I've got some other figures that kind of illustrate that a little bit more. But again, just towards the bottom of that chart, you then see some of the other reprocessing commercial facilities around the world. In France, the UK I've already mentioned, Japan, which is going live kind of imminently almost, and then in Russia. So this is just again to show you kind of some schematics, and I'll show you some photographs in a second of what this thing looks like. But again, just stepping through receipt and storage, just where the fuel is brought in from overseas or from elsewhere, from the reactors, brought into the reprocessing plant. The cask is then loaded into a spent fuel pool. The pool then provides that radiation barrier and the heat barrier. Then the fuel is removed and stored until it's ready for the reprocessing plant, and then that's then lifted up to where it can be sheared, chopped up, and I'm going to show you some photos of that shortly. Then the chemical separation takes place in stage 3 there, then purified, because the uranium goes one way, plutonium another. Then it's it's purified and then stored if necessary, and then the waste products go a different direction. So in terms of dissolving the fuel, as I said, once you've actually chopped the fuel up and you've now exposed those pellets, it's a chemical reaction that's used to dissolve the fuel, and it's typically nitric acid. And when you look at some of the chemical processing that's involved in reprocessing, you realize just how difficult this whole process actually is. You've got something like 7.5 molar nitric acid used at typically up to 100 degrees centigrade in a very, very, very strong radiation field. So all of this is done behind tremendous shielding, and so when you start thinking about the heat, the dose, the chemical interactions, there's an awful lot to take into account from a safety perspective. There's also potential risk of that material being concentrated and going critical, so they actually do things like put gadolinium poisons in there to prevent the risk of criticality. And in fact, for other reprocessing options, for example, like the thorium fuel cycle as well, there are other chemical reagents that may come into play, something as strong as hydrofluoric acid, which is particularly corrosive. So you can you can particularly again see that some of the challenges that you can face in a reprocessing facility. So the way this actually works is, and again, it's easier for me to show you in a diagram, but how this whole chemical process works, it's a liquid extraction process where you've got two phases, and those two phases being immiscible, it's that then the material after kind of gets transferred across from one phase to the other phase. towards the solute, the material that we want. And again, I show that in a picture in the schematic. It's much easier to see. But the first thing is that we first of all separate the uranium and plutonium material from the fission products and the minor actinides, so they go one side, one way, and you'll see that in a second. And then once we've done that, we've got these two kind of bulk materials. We're then able to concentrate on the separation of the uranium and plutonium from each other in a next stage of the process. So again, the easiest way to see that is in this process here. So at the bottom we've got the aqueous solution. You've got that nitric acid and all that other, and the fission products and the uranium and the plutonium and the minor actinides all mixed together, and then you add to it an organic solvent on top, something like tributyl phosphate and odorless kerosene are the two typical chemicals that are involved in this. And what then happens is, by then those two being mixed, you get this this solvent extraction process where the material that you want, the uranium and the plutonium, is drawn across into the upper phase, therefore leaving the fission products and the other materials behind in the lower half. So that's what you're seeing again here. Just again to reiterate, the extraction in TBPOK, where the uranium plutonium goes one way, the fission products go another. Then what you can then do is then change the acidity of that separation material. You can then have the uranium go one direction, the plutonium drops out of that, and then you can purify. And again, I'm not going to go into the details, but you can just see, hopefully see the various stages. But this is what I just wanted to show you, some of the pictures inside of one of the reprocessing plants. This is the Thorpe reprocessing plant in the UK. So this is what's known as the shear cave, and hopefully you can see on the right hand side what appears to be a kind of a V-shaped kind of guttering that goes off into the distance. So what happens is the fuel assembly is brought up from the spent fuel pools down below, brought up and then lowered into that V-shaped gutter. And that holds the fuel assembly in place for it to then turn to then face the shearing blade. So what you then see here is the fuel assembly in that gutter that I was just describing, that holding position, and it's now being lined up, ready to be faced and pushed through the hole on the other side, where the shearing blade will come down and begin to chop the fuel. Now what's interesting is, usually when I always visualize chopping, I think of something quite kind of quick and harsh like that. But if you think this is, in fact, is more like a knife through butter. It's more like where it's a continuous pressure being applied to slice through the fuel. It's not a big chopping mechanism. And what you see just about, I hope, in the photograph on the right hand side, you hopefully can just about make out a fuel assembly here, and that's the blade coming down to begin to chop the fuel. So at the top of this chute up here is where that fuel is being chopped into typically 1 to 2 inch pieces, and so that will then fall down from the above down into the collection basket at the bottom, and that's where the dissolver is waiting. And the dissolver, just to illustrate, is almost like basically a stainless steel basket, of which that's immersed then in the nitric acid. And so when that's loaded into nitric acid, the material, the fuel, is dissolved and comes away from the cladding pieces, the elements, the hulls as they're called. Excuse me. And then that's dissolved up, and then when you lift out the basket, the hulls, the cladding is left behind in the basket, and in the liquor that's behind then is your uranium, plutonium, minor actinides, fission products that are all dissolved. So once you've then taken your plutonium and uranium in one direction, you've cleaned those, you're going to purify those for future use. You've then got all the other material that you no longer need, things like the minor actinides and the fission products, that you then vitrify in a glass. You basically mix them with a liquid glass, and that will then be put into a container, sealed up and then decontaminated, and then down. That's the material that eventually goes down into the repository rather than the full fuel assembly, this new dissolved up set of material. And again, that schematic there shows that, what I just outlined there. And the high level waste, as it's called, those minor actinides and fission products go into a container. Typically, this again just to illustrate size, just to be 100% clear, if that really was high level waste, she wouldn't be standing next to it. It's incredibly active. You would be dead before. I think people say if you run from an infinite distance, by the time you get to it, you'll be dead anyway. So that's clearly something not to be messed with. But what's interesting though is that if you look at the picture on the right hand side, that's actually the high level waste store at Sellafield. And I've actually stood on top of that on 2 or 3 occasions during my career. That below your feet there is those canisters stored on top of each other. I'll show you a picture in a second. And again, but the radiation field, because of concrete barriers and so on, are perfectly fine. You can stand on top of that area. So here is a schematic of what you've just seen. So this is the level where those people were standing up here on the top in the plant area, and then below them are those individual canisters that I just showed, and they're stacked on top of each other as shown on the right hand side, and that's just natural air circulation is used. And at Sellafield there's something like 50 years of high level waste sitting there from not only UK reprocessing but from reprocessing around the world. So the spent fuel volumes are incredibly small. The estimates is, and you can do the calculation yourself, but the estimates are that if all of your electricity energy demands came from nuclear, the amount of high level waste that you would generate in your own personal lifetime would fit inside a small paint canister. So that's why it's such a small amount of volume. But as I mentioned, there are other wastes that come from nuclear, and so there are other processes needed to deal with the other wastes, whether that's decommissioning wastes, the intermediate level waste, which are these hulls, these material and mechanical pieces, and they're typically just overpacked with a cement or a grout, and then again will be sent for ultimate disposal. But still, again, you still need that repository. And one thing I'll underline at this point is it doesn't matter whether you are going through for a once-through fuel cycle or a reprocessing fuel cycle or the ultimate best ever fuel cycle you can think of, you will always need a repository. The only difference is how big that repository will be needed. So that's a kind of introduction to the reprocessing side. So I'm going to talk about the recycling side. Typically, I think I've touched on most of these already, but why recycle? Because we want to get the fissile material. And this really harps back to the 1970s and the oil crisis. There was a big push for nuclear and big push for nuclear, and therefore a concern about demand on uranium ore. And so the concern then was, well, how are we going to address that? And fast reactors and recycle was the main driving force towards that. And despite the oil crisis never quite coming to fruition as everybody expected or feared it would do, several countries did start out on that route: Belgium, France, Germany, etc. And so they are now looking at, or actually are doing, particularly in those countries, have looked at and are recycling their plutonium from that interim kind of reprocessing stages. They're reprocessing and recycling that plutonium in existing reactors. So that's that modified open fuel cycle, limited recycle stage that I mentioned earlier. And again, the UK has something like 100 plus tons of separated plutonium, with nothing currently planned apart from hopefully they'll put it in future reactors. Important point to note here though is that if you only recycle the plutonium and the reprocessed uranium in light water reactors, you will only see about a 20 to 25% improvement in your ore savings. To get that huge, tremendous improvement, you really do need to go for full multiple recycling fast reactors. So that's why that isn't quite getting to the full potential. The other thing just to bear in mind is that on the current uranium markets, the reprocessed uranium can be economically competitive with buying uranium ore fresh. So again, in France, there's a lot of actually that's already going on. They are recycling not only their plutonium but also their reprocessed uranium. The thing is though, not all plutonium is created equal. So you often hear people talk about weapons grade plutonium or bomb grade plutonium or civil grade plutonium and all these other things. And it is different, and just want to give you a very quick explanation as to why it is different. So plutonium is generated in a reactor. It's the only place it's generated. It's not natural, and it's captured. It's produced by a uranium-238 neutron capture. So uranium-238 captures a neutron, becomes a Neptune-239, decays to plutonium-239, 238, sorry, and then it can go up through that chain, and it can capture the 238, 239, Plu-240, 241, 242, and so on. So the chance of that happening, the chance of that neutron being captured in that U-238, is very much dependent on the reactor environment that it's in. And it also depends on how long the fuel is in the reactor for, because the longer it's in, the more chance of capturing a neutron, and therefore the more plutonium is produced. But if you leave it in too long, then that plutonium begins to fission, and then the plutonium composition turns over. And also, depending on the initial enrichment, is it natural or enriched fuel that you originally put into that reactor, that also affects it, because you've got different amounts of U-238. And the relevant abundance of all those plutonium isotopes is what's known as the plutonium vector. And the combination of the Plut-239 and Plut-241, which are the fissile isotopes, whereas all the even isotopes are neutron absorbers, that affects the plutonium quality. The quality is governed by how much fissile material we have. So just to illustrate that, if you look at weapons grade plutonium, it's pretty much all plutonium-239. And again, all this material that's in this talk, including this slide, is unclassified, so don't worry about any information in there. I should have underlined that at the beginning. So the other thing as well is the weapons grade plutonium majority is Plut-239. If you look at the Magnox fuel in the UK, you look at, again, quite a good fissile material, because that used to be the source of the UK's plutonium for their bomb program. So again, it's a nice reactor that generate plutonium. And also then you see how those commercial reactors like the pressurized water reactor or the advanced gas cooled reactor, they notably affect the fissile quality, the 239 plus 241. So why is that important? Well, the other thing you should also bear in mind is that the plutonium-241 concentration will also change with time, because Plut-241 decays to americium-241. And americium-241 is no longer fissile, so you actually over time lose your fissile quality. And also the americium-241, unfortunately, is also a neutron absorber. So over time, if you've made a strategic decision to separate plutonium to reuse, it actually makes more sense to use it earlier, because you're going to be losing your fissile material over time. And unfortunately, the americium-241 is also a dose consideration, a dose issue. And so again, if you're not careful, you're going to end up with a situation that you can't actually use it any longer in your fuel fabrication plant. So typically, these are just some kind of examples. As I said, the kind of typical concentrations you'll see. And this just shows you how, depending on your original plutonium that you've got, how much americium will build up over time, and why it does or does not become a concern. So if you look at the second line from the bottom, which is the Magnox plutonium, the UK is able to store its plutonium for a long period of time without much concern about americium ingrowth, and therefore making a strategic decision about recycling plutonium is not such a tight timescale. Whereas if you're France, for example, and all your reactors are pressurized water reactors, then after only something like 10 years, your americium ingrowth has got to typically 3, 4, 5%, and that's certainly higher than fuel fabrication plants are able to tolerate. So you need to do something more quickly. So what they do is they load it into what's known as MOX fuel, mixed oxide fuel, and that's a combination of plutonium, which makes about 10% of the fuel, and the other 90% is depleted uranium. The material that, when we have enriched uranium, goes one way. The other way, the depleted, is what's the byproduct of the enrichment process. So depending on how much energy we need to get out of our fuel, we increase the plutonium content. Tails uranium I mentioned is depleted uranium. We blend those together, we press them, we make it into a new fuel. And again, I'm not going into the details. Again, just conscious of the time. But you just have to be careful with this plutonium as well, because it's also now with plutonium, they're heat generators. So you have to be a little bit careful in terms of the fabrication process and so on. But the key point here really is that if you were to look at a fuel design, a fuel element that had plutonium fuel in it, MOX fuel in it, versus one that had uranium only in it, you couldn't tell any difference. They're actually identical mechanically. The only difference is, though, in a MOX fuel fabrication plant, because of the dose from the americium, because of the dose and the heat from the plutonium, you need to make sure the shielding in place. Glove boxes become incredibly important. There's a lot of automation in them, less hands-on operations compared with the uranium facility. And all of that, plus all the additional security that's necessary and so forth, makes, in fact, MOX fuel very much more expensive than uranium fuel. And that's why, again, it doesn't seem to make sense today to go forward with the MOX fuel as on a commercial basis, unless you've already decided to separate out for a different reason, back to the things I said earlier. So again, this unfortunately is an old slide, because the Sellafield MOX plant is actually now closed. The UK government decided to close the facility, but on the photograph on the right hand side, the red and black building on the right hand side is the end of the chemical separations plant in Thorpe that I showed you the photograph earlier. And the building that comes out to the left is the Sellafield MOX plant. So the MOX fuel fabrication plant is almost, inextricably linked to the reprocessing business, because the product that comes out of the reprocessing is plutonium, and that's the feed material straight into your fuel. So this is, again, I'm not going to go into the details, but just to demonstrate the process is you mix the uranium and the plutonium together, you kind of mill it together, and then you add pore formers and you produce pellets. And again, this is just to show you some photographs of what these things look like. And again, I'm not going to spend time on this because, again, it's just some photographs to illustrate. But again, for those people who may not have seen what fuel pellets look like, it's pictures of fuel pellets being pressed. You're seeing the dies on the right-hand side that press those pellets. And then, as I mentioned, everything's behind glove boxes. For anybody who's seen a fuel fabrication facility for uranium fuels, you don't see all this kind of glove boxes. You can see things much more clearly as to what's going on. It's not all inside containment, as you're seeing here. So again, you can see how much more the operations become difficult because of all the manual detachment that's needed. You need either remote handling or inside glove boxes and so on. So things like maintenance become very difficult on these things. But once it's inside a fuel assembly, as I said, there's no difference. And in fact, more often than not, you can handle that. Apart from you'll feel it's a little bit warmer on the outside just because of the plutonium decay. The guy on the right-hand side is wearing gloves. Just to be clear, he's wearing gloves not because of concern about contaminating himself. It's concern about him contaminating the fuel assembly. Because what we don't want to do is people to leave greasy fingerprints all over a fuel assembly. It's going to go into a reactor because that can affect the reactor performance. So it's actually protect the fuel assembly, not him. Again, I'm not going to go into the details because this is more my background in reactor physics. That's why I threw these in there, because I find it quite interesting. But really the important thing is that MOX does actually have an impact on the reactor operations. It's not something that you can just load into a reactor without any consideration. You have to do new safety analysis. There are limitations on what you can do. And the reason being, unfortunately, is that plutonium preferentially absorbs neutrons. So you've just fissioned uranium and plutonium. You've generated these neutrons that you want. But unfortunately, the plutonium itself preferentially absorbs those neutrons that you may need other materials, such as the control rods and the shutdown systems of the reactor, to utilize those neutrons. So unfortunately, what it means is they reduce the absorbing worth of control rods, of the coolants, of the burnable poisons, and so on. And again, I'm not going to go into this detail. This is just for your broader knowledge in a sense. But also things like how you control the reactor using delayed neutrons, they're affected because the number of delayed neutrons is reduced. You can mitigate some of the effects. You can do things in reactor operations. You can do things in your safety analysis. You can put in extra control systems. But generally what people do is they just simply limit the fraction of MOX fuel that's allowed in the reactor. So normally it will be 100% of the reactor is uranium fuels, of course, but it tends to be we don't load 100% of the reactor as MOX fuel. If you look in France and other places, typically 1/3 of the reactor is loaded as MOX fuel and 2/3 as uranium fuels. Again, the details aren't so important, but the fuel performance itself is also affected by the presence of plutonium. And again, I'm not going to go into the details. But the key takeaway again from all of this is that generally MOX fuel A costs more and B has an operational impact on the performance of your reactor that you have to mitigate against by a range of things that I've listed here. So that's the takeaway from this really, is it's not quite just as simple as using uranium fuel. And again, I'm not going to go into the detail, but the manufacturing process is much more complex, because usually in a uranium fuel assembly, certainly for a PWR, we only have one enrichment. So what it means is you can manufacture all of your fuel rods exactly the same enrichment, same pellets, same everything. But unfortunately with MOX fuel, that's not the case. Because of the MOX and uranium kind of cohabiting in a reactor, you have to have a much more complicated plutonium distribution in your fuel. So again, I'm not going to go into that. This is just to illustrate the differences for PWRs and BWR fuel assemblies. The one thing I would say though is that the plutonium and therefore the MOX fuel does have a much higher spontaneous fission neutron output than uranium, and because of that has a much higher decay heat. And because of all the decay heat considerations, what you end up with is something like a factor of 3 or 4 more heat in a MOX fuel assembly than in the uranium fuel assembly. So that has significant implications on the spent fuel pools at the reactor, but also on your repository performance if you are considering putting MOX fuel in your repository. So again, there are spent fuel issues to be concerned with. I've already touched on this before, so I won't spend time on this, but just to reiterate, MOX is much more expensive than uranium, typically 2, 3 or 4 times. But what if you've decided you want to go ahead with recycle for a whole range of other reasons, and plutonium is free issue once it's separated, it does give you the benefit because it's free. You can kind of load more and more and get more energy out of your fuel. Also, the price of plutonium is insensitive to the price of uranium ore. So if you are sitting on a stockpile of plutonium like the UK and France, what it means is that if suddenly there's a huge dash to uranium and ore prices for uranium spike, which they have done in the past, you can kind of offset those costs with a bit of a strategic reserve by reusing your plutonium or indeed your reprocessed uranium. And again, overall, as mentioned about reducing the volume on the repository and so on, and the impact there. You can also reprocess the uranium. There's a lot of uranium around different parts of the world, and again, this is just to illustrate from a report from the Nuclear Decommissioning Authority, the NDA. There's a range of tails uranium, depleted uranium, reprocessed uranium, and again, the isotopics that you see in all of that fuel in that reprocessed uranium depends on a range of factors, exactly the same factors as the plutonium isotopics. And again, just an illustrative example, if you look at the uranium composition of the reprocessed uranium, typically it's dominated by U-235 is left about 0.9%. You started with about 4 or 5 when you first put the fuel in the reactor. It's now fissioned and depleted down to about 0.9, but you've also produced the other uranium isotopes. It really doesn't have a huge effect on the reactor itself, so that's quite useful, but you do have to be careful because the 234 and 236 actually absorb neutrons. They don't contribute to the fission, so you need to over-enrich the U-235 to compensate for that extra. And the other thing, this becomes of interest to the thorium fuel cycle also, is that the U-232 byproduct that comes from this has a quite a significant daughter product, thallium-208, that has a very high gamma dose, like 2.6 MeV gamma. And so what that means is if you're considering recycling uranium, you then need to think about the shielding implications on your fuel fabrication plants. And that effect increases with time because over time you'll grow in more U-232. And also what it means is now that your enrichment plant and all of your standard uranium fuel cycle plants also have now been contaminated with these materials. So you can recycle. It's known as enriched reprocessed uranium once you re-enrich it into a new product. There are other options to maybe use that material down blending HEU from surplus weapons program. And in fact, there's a program of work currently going on with Canada and also in South Korea, where they're using the reprocessed uranium from light water reactors and are able to load that directly into a CANDU reactor, because CANDU reactors don't need enrichment, they just need a natural background, 0.7% U-235. Again, not going to talk about this. This is just to illustrate some of the points I've already made about the additional costs and the violation of limits and so on. So I'm not going to go into this. It's probably a bit more too detailed than you need. So just to come back to the reprocessing and kind of cover this from a non-proliferation and safeguards perspective. There are a whole range of obviously concerns with non-proliferation and safeguards. Usually it's about material attractiveness, so that's one we kind of focus on. But you have to bear in mind that if you look at the reprocessed uranium that comes from recycling, as I said, the U-235 content now is very low, typically 1% or less of U-235, and you need isotope separation, re-enrichment to take that any further. However, with the plutonium that comes from that, typically you've got about 50 to 80% fissile. And again, if you look at Chuck Bathke's work on the figure of merit and the material attractiveness, he demonstrates that that material, that plutonium quality, is still sufficient for a weapon, still weaponizable, has material attractiveness. There are smaller scale operations other than commercial reprocessing that can be used to isolate just a few significant quantities. And again, they're more likely to be used in commercial reprocessing plants. And again, that's just something to bear in mind. There's often a big difference between research programs that are going on around the world and significant commercial reprocessing plants. So again, just be bearing in mind that the different techniques can be used depending on the application. But the conclusion from all the studies, and this Chuck Bathke one I keep alluding to, is that really plutonium has no intrinsic safeguards. Because plutonium is plutonium, it can be used in a weapon. You therefore do need to have safeguards. But because you've got plutonium in all of the fuel cycles, irrespective if you're separating it or not, you still need safeguards. You still need safeguards and security for every single fuel cycle. And again, guns, guards, gates, and all the other things that go along with that. And as I said, since all recycled fuel cycles and all fuel cycles end up with some form of separated fissile material, then it holds true for all fuel cycles. You need safeguards in all fuel cycles, regardless of whether you reprocess or not. Just going back to what I said before, there are a range of options though where people don't want to, for a variety of reasons, safeguards reasons and so forth. They do not want people to have separated plutonium. So there are technologies to try and keep those together. And again, that's just to reiterate what I said earlier, just coming back to that kind of full circle, that these are some of those advanced techniques. But there is this concept called safeguards by design. So in a sense, the chemical processing is a safeguards by design by not separating materials into different streams and trying to keep everything together. There is also a safeguards by design in this context where if all of the processes where you could separate out and divert material, if all of those processes are kept in one facility, so that's everything from the time the spent fuel arrives to the time you shear and then separate all the material and then make new fuel, if all of that is inside one controlled area, then literally from a safeguards perspective, all you need to be monitoring is how many spent fuel assemblies come in and how many fresh new assemblies go out. And monitoring positions through all of that then minimize the opportunity for diversion of that material. And that's what you just see here, this idea of co-location and integration of the separation streams and also the new fuel assemblies. So again, fissile material entry removal in the form of is large and heavy fuel assemblies, so it's kind of easy to account for, and B, it's hard to divert those large assemblies. And then as long as you are continually monitoring and surveying the wastes and the personnel exiting the recycle plant, then it's easy for you to make sure that nothing's being diverted. And then also you don't have fully separated plutonium, so all of these potential risk elements you're avoiding by safeguards by design, building that into the flow sheet that you start with. So to conclude, just a brief summary and conclusion. Despite what people may think, the US once-through fuel cycle is not the only option. There are many other options out there. As I mentioned, many countries around the world, such as France, UK, South Korea, Japan, Germany, Belgium, many others, are doing other fuel cycles that involve separation, reprocessing, and then recycle. Not everybody has taken that all the way through to ultimate recycle in fast reactors, but that's the avenue, the direction that many people are going, including indeed the US, as I mentioned, looking at future fuel cycle options. But again, people often point to these advanced fuel cycles and say, well, you're not able to demonstrate them. And that's true. And in fact, unfortunately, we're not yet able to also demonstrate the once-through fuel cycle because we haven't actually put any spent fuel in a repository. The closest people are Sweden and Finland. They're getting pretty close to doing that, but they're still not quite there yet. Something that I just wanted to mention in wrap up is that often people think that the US has a moratorium and is a ban on reprocessing because of the Carter administration back in the 70s. But that's actually not true. That did happen, but in fact in 81 Reagan lifted that moratorium, and so reprocessing is actually not banned in the US. It's something that people either don't care to realize or don't follow the history and read that part. But basically, reprocessing is not banned in the US. It just makes absolutely no commercial sense. That's the main reason. So the other thing as well is back to the Carter administration, though. The idea was that if the US leads by example and doesn't reprocess, then nobody else in the world will reprocess. But as my list there suggests, that didn't work out quite as expected. Because despite the US not reprocessing, many other countries did reprocess, and they are continuing to reprocess. And added to that list is China, India, South Korea, and that list is probably going to grow. So I think because of that, there is potential that the US may think about reprocessing or future fuel cycles at least, because recognizing that as the world grows and energy demand grows for nuclear at least, then it puts in a new pressure on uranium ore and therefore it makes sense to recycle potentially if the economics is right. There are a huge range of different drivers likely to affect the future's choices. As I mentioned, as I said, the US policy on not reprocessing has not limited the impact on the rest of the world's choices. So I think that's something for us all to learn, is that the other countries will do what they see as right for their policy, and understanding what their policy is very, very important. Another point that I've underlined hopefully a few times is there is no such thing as a proliferation resistant fuel cycle. People will tell you, advocates of certain technologies will tell you, for example, thorium fuel cycle is proliferation resistant. It is not. U-233 is the most fissile substance known to man, and the IAEA treat the U-233 classification exactly the same as plutonium, in fact higher than enriched uranium-235. So there is no such thing as a proliferation resistant fuel cycle, simply because we need fissile material in a fuel cycle. That's how we get energy out. So if there's fissile material, we'll need safeguards, and we'll need security, and we'll need monitoring. But engineered safeguards and safeguards by design as a concept can be used to provide additional and beyond this kind of standard safeguards approaches, and ensure as a whole level of barriers and levels of monitoring. But really the cost of implementing any future fuel cycle technology, recycle or others, again thorium, plutonium, whatever it may be, it will be a significant challenge for the industry. It's a significant challenge in terms of cost. It's a significant challenge in terms of risk. And as you've probably seen around the world, there are a lot of talk about new nuclear energy, but it's limited because of the cost and the risk that people don't want to take, because the economics just doesn't stack up right now. So for the significant investment, it's unlikely to happen for a while, and probably will need therefore governments to intervene and have government programs rather than on a commercial basis alone. So with that, I think that's my last one.